You've probably heard the term neural network thrown around a lot. I mean, they're everywhere. They power your phone, they protect your bank account, they even help doctors out. But what are they really? What's actually going on inside these incredibly powerful, kind of mysterious artificial minds? Well, let's pull back the curtain and take a look. So let's start with a question that seems simple, but for a computer is actually incredibly hard. How does a computer learn to see a dog? For you and me, it's instant, right? We see all these different breeds, weird angles, different lighting, but our brain just knows, yep, that's a dog. A computer, though, it just sees a grid of numbers representing pixels. To a machine, these three pictures are completely different sets of data. So teaching it to find the abstract idea of dog and all that noise, that was one of the biggest challenges in the history of AI. To crack this problem, the AI community realized they needed a totally new way to teach these machines. And the answer, it turned out, wasn't just a smarter algorithm. It was smarter data, a lot more data. What if they could create a massive, shared library of images, all neatly labeled by humans? This idea led to a project on an incredible scale, and a yearly competition that would end up changing everything. And the effort behind this was just massive. The project, called ImageNet, kicked off in 2007. And to label millions and millions of images with things like dog, cat, or car, the team used crowdsourcing, paying thousands of people online small amounts of money to help out. By 2009, they had this incredible dataset, which set the stage for a real breakthrough moment in 2012. And that breakthrough was a neural network called AlexNet. In 2012, it entered the ImageNet competition and just completely blew everyone away. I mean, look at this. The next best program had an error rate of over 25%. AlexNet dropped that all the way down to just 16%. In the world of AI research, a 10-point leap like that isn't just a step forward, it's a full-blown revolution. To put that in perspective, AlexNet was getting only 3 out of every 20 images wrong. If this were a school test, it was scoring a solid B, while every other approach was barely scraping by with a low C. This was the moment everyone sat up and realized these new learning systems were the future. It's what sparked the deep learning explosion that we're still living through today. Okay, so AlexNet proved that neural networks worked, but that doesn't really explain how they work. So what is actually going on inside one of these things? What does the architecture of an artificial brain even look like? At its core, a neural network has 3 main parts. You've got the input layer, which takes in all the raw data, like the brightness value of every pixel in that dog photo. Then you have the output layer, which gives the final answer, something like dog or not a dog. But the magic, the real thinking happens in between, in what are called the hidden layers. So here's the crucial idea. The neurons in these hidden layers aren't just simple on or off switches. Each one is doing a little bit of math. It takes in numbers from the layer before it, crunches them together, and then passes a new number on to the next layer. It's this constant process of mathematical transformation that lets the network learn complex patterns. Let's go back to the dog picture. The first hidden layer might just learn to see simple things, like edges or curves or a patch of color. The next layer then combines those simple ideas into something more complex, like the fuzzy texture of fur or the specific shape of a floppy ear. Then an even deeper layer might learn to combine the concepts of nose, ear, and fur until finally the network can confidently recognize a dog. It builds up its understanding one layer at a time. Okay, so that's the structure. But when a network first starts out, all its internal math is just a bunch of random numbers. It's basically just guessing wildly. So how does it get from that random noise to making really accurate predictions? How does it actually, learn? Well, the process is called optimization. And a good way to think about it is like tuning a massive, complicated instrument. Every single connection between neurons has a weight, basically a little knob that controls how much influence one neuron has on the next. The goal of optimization is to find the absolute perfect setting for all of those knobs, to tune the entire network until its predictions are as accurate as they can possibly be. Here's a really cool way to visualize this. Picture a huge, sprawling, mountainous landscape. The altitude at any given point on this map represents the network's error rate, how wrong its guesses are. So higher up on a mountain peak means lots of errors. Your job as the trainer of this network is to find the absolute lowest point, the deepest valley on the entire map. That one single spot represents the perfect set of weights for the network. But this is super tricky.
The network, our little explorer, might find the bottom of a small valley and think, hey, I'm done. This is the lowest I can go. That's what we call a local solution. It's good, but it's not the best. The real prize is the global solution, the deepest valley on the whole map. Getting stuck in these smaller, local valleys is one of the biggest challenges in training AI. So how does the network find its way down into the valley? It uses a clever algorithm called backpropagation. Basically, after it makes a guess and sees how wrong it was, the network works backward from that error. It assigns a tiny bit of blame to each neuron that contributed to the mistake, and then it slightly adjusts their weights to do a little bit better next time. It's literally learning from its mistakes, making thousands and thousands of tiny adjustments.
All right, so now that we've kind of unpacked the mechanics, let's bring this all back to our daily lives. Because this technology isn't just stuck in a research lab somewhere, it is already all around you, often in ways you might not even realize. You know when your bank sends you a text about a suspicious transaction? That's a neural network spotting a pattern that doesn't look right. Ever talk to a voice assistant like Alexa? A neural network is translating your speech into commands. From suggesting who to tag in your photos on Facebook to helping doctors analyze medical scans for signs of cancer, these systems are quietly running in the background of our modern world. But it's not all perfect. There are some really big challenges. First, there's the black box problem. As these networks get more and more complex, their internal logic becomes almost impossible for a human to understand. So if a network denies someone a loan, we might not get a simple answer as to why. Second is something called overfitting. This is where the network learns silly coincidental patterns in its training data, like a famous fake correlation between divorce rates and margarine sales, and then makes really strange errors when it sees new, real-world information. And this all leaves us with a pretty critical question, doesn't it? We've built these powerful digital brains, and they're starting to make more and more decisions that really affect our lives, our health, our finances, you name it. So as we hand over more of this responsibility, the biggest challenge probably won't be making them smarter. It'll be making them fair, transparent, and ultimately something we can actually trust.